Okay, good afternoon, Seg 1A. This is a quick lesson on torque or moment. All right. Okay, you know about force already. That causes translation motion, which is up, down, left, right. So, and if you want balanced forces, then you have equilibrium. So let's say 10 newtons that to the right and 10 newtons to the left. And that's what we call static equilibrium. Same thing with torque. Okay, torque causes rotation. Now it's a little easier. There's only two types of rotation, clockwise and counterclockwise. So for example, if I throw this marker somewhere from point A to point B, it's not just gonna travel from point A to point B. It will spin also when it gets there, just like if you shoot a basketball. So the basketball will go to the basket, and at the same time it is also rotating or spinning. Okay, all right, so that's torque. Now, the equation for torque or moment is tau, a Greek letter, okay, tau equals to R cross F, R times F. R is the distance, so the distance is in meters, or kilometers or centimeters, from the pivot to the force. And F is just the applied force. So F is in newtons, R is in meters, so it's meter times Newton, but conventionally we write Newton first. So Newton meter, so that's the unit of torque or moment, same thing. Okay, so you can call it moment if you want to. A lot of Americans use the word torque. And when you look into the industry, to like automotive industry, then they use a lot of word torque. Okay, example of torque. A door. When you open a door, it rotates. Okay, it doesn't translate. Okay, there's no translation motion. There's only rotation motion. It rotates back and forth, which we call clockwise or counterclockwise. Now, where you push the door will determine how much torque you have. So most people will push the door furthest away from the hinge. This gives you the most torque, this point, okay, furthest away from the hinge. Okay, now you push it close to the hinge, you don't get a lot of torque, and it becomes harder to open the door, especially a heavy one. Okay, so again, torque depends on the distance from the pivot to the force. The force is where you push your hand, where you put your hand on the door and push it. So let's say you put your hand right here. So that will be the force applied to this point, and the R, which is the distance, will be from the pivot point, which is the hinge, to the force, where you place your hand. Another example is a wrench. Okay, a wrench, so you turn a nut right here. There's a nut right here, so you turn it. You can either turn it clockwise or counterclockwise. Okay, so you turn it clockwise, it will go in. Turn it counterclockwise, it will come out. Now, you probably want to apply the force furthest away from the nut. Okay, so the farther you are, the more torque you have, because that's bigger distance. So the R increases. Okay, and the F is just how many newtons you push it. Another example is the engines. Okay, the engines in your car, the engines on the boat, the engines on the plane, on any mechanical engines, you have rotational part. Even a bicycle, you have torque when you pedal your bicycle. Okay, so anything that rotates, any type of engine, doesn't have to be complicated engine, can be simple engine. Lever. This is called lever, employs the same principle. So this will be the pivot point right here, pivot point. The pivot point is a point that doesn't move. So we call it pivot, P-V-O-T, pivot point. Or sometimes the Brits like to call it fulcrum. Okay, fulcrum. Yeah, you also see that in the movie, I don't know, Mission Impossible, fulcrum. So pivot point, so you use a lever, you probably want to apply the force as far away from the pivot point as possible for the maximum torque to lift this rock. So this is a rock, a heavy rock, and that's a pivot. Here, the pivot would be right here. It's a point that doesn't move. That's the pivot. Here, the pivot would be the hinge. Pivot. will be the hinge. Okay. All right, let's apply it to a real problem. Now this is a meter stick. Okay, it starts with 0, starts from 0, and here's a pivot point at 62.0 centimeters. Okay, and here's at the end, which will be 100 centimeters. So you have a mass hanging on it. Okay, and everything you do in Sec 1 will be static. Static means it doesn't move. So that means it has to be balanced. Okay, so this question asks you to find the mass of the meter stick. Finding the mass of meter stick means that you have to put the mass of meter stick here somewhere. Well, as you know from center of mass, so the mass of meter stick is going to be exactly in the middle of the meter stick, which is at the 50 centimeter mark, 50 cm mark. So let's put the mass of the meter stick right there, m, but we don't know what it is. We have to find out. Okay, so now static equilibrium, which will be the same with all the questions that you will see. So nothing will move. So nothing will move, that means the torque. So this fancy T is called tau. It's a Greek letter tau. So you can use T, that's fine, or you can use tau like the rest of us if you want to. So tau clockwise equals to tau counterclockwise. So this is the equation you will use to solve all these rotation problems, all these moment problems, or torque problems. So now, if you look at these two masses, one mass is going to cause it to rotate clockwise. It's this one. Okay, so if you just focus on this one, it will tend to pull this meter stick down. So that's clockwise motion, same direction as the clock, the hands of the clock. And this mass, the mass of the meter stick, tends to pull it this way in the counterclockwise motion about the pivot point. Okay, remember pivot point, this point doesn't move. Anything on top of this point doesn't move. Okay, so this is clockwise, this is counterclockwise moment. Okay, so let's look at the clockwise first. Clockwise is R. Let's put clockwise R times F. This is counterclockwise R times F. So R, so you find the R for clockwise. So from 62 to 100, so this is 100 centimeter mark, 100 cm. So from 62 to 100, that's about 38. So 38 cm. So let's put 38 cm. Okay, don't worry about the unit, can be cm or meter, but they will cancel out with the unit on this side. Times the F. So the F is, we have 24 gram. So let's multiply by 10. Multiply by 10 to get the weight, because you want everything here to be weight. This is mass, mass. Remember, mass times gravity equals the weight. So mg. So 24 gram times 10. So equals to, so you have only one mass that will cause clockwise motion, and you have another mass that will cause counterclockwise motion, which is m. We don't know m, so let's write the R first. So the R from 50 to 62 is 12 centimeters. So let's write down 12 cm times m times the g. The gravity is 10. That's it. So as you can see, the gravity will cancel from both sides, okay, and centimeters cancel from both sides, okay, and you have 38 times 24 on this side, gram equals to 12 times m, and then solve for m equals to 38 times 24 gram divided by 12. 12 goes into 24 two times, 38 times 2, which will be 80 with 76 gram. So you have gram left right here. So 76 gram. Okay, 38 times 2, that should be 76. Okay. All right. So that's the answer. So m equals to 76 gram. Okay. So it's pretty easy actually. Here's the calculation again. So R, remember the R. So this will be the R. So 38 R times F. So F would be this mass times gravity. That would be F. So, and here's the other R, from 50 to 62 times the F. F will be this mass times gravity. Okay, but you don't know this mass yet. The 76, you don't know that yet. So just write M times 10. Okay, and here's the calculation again. Again, you use this over and over. So the key here is to recognize that there's the mass right there acting in the middle of the meter stick, which is the center of mass. Okay, the problem doesn't show you, but you're supposed to know that. Okay, now if I were to put another force right here, right there, so another force, let's say 20 newtons or whatever, so this force will cause this meter stick to go counterclockwise. So then you have two torques, okay, two torques on this side counterclockwise and one torque on this side clockwise. So just depends on how many. You just keep adding. Okay. Now if I have, so let's say I don't have that, but I have this force instead. It acts parallel to the meter stick. Since this force acts parallel to the meter stick, it doesn't generate any torque. So this force causes zero torque. So you don't even have to include this force in your calculation. As long as it goes through the pivot point, it generates no torque. Just like going back to this door, if you were to open this door by pushing it this way, okay, against the hinge, the door will not open, will not move at all. So either you push it this way, perpendicular to the door, or you pull it. Push or pull, cannot go this way. If you go like that, or if you go like this, okay, so these two forces will generate zero torque because they're going through the pivot point. They go through the pivot point. So you can always extend the force, the line of force, all the way. Okay, all right, so that is the moment in 10 minutes or 12 minutes.